Okay, so let's try to cover the theory of relations. Let's go. So a relation is just a subset of C cross D, essentially, or any Cartesian product. That's pretty much it. So it's actually a far simpler definition than what a function was, but functions are in a way more intuitive. So there's that. Okay, it is an example. Now, yeah. So equivalence relations. So X, it just has three properties, and that's pretty much all you need. And that's pretty much all you'll need for the two. So let's just write them down for all X in, so it's defined on a set, right? So for all X in A, X is, that's reflexivity. This is the symbol for the equivalence relation. Ultimately, they're just symbols for sets. For all X comma Y in A, X, Y implies Y, X. For all X comma Y comma Z in A, X, Y, Z, Y, Z implies X, Z. That's transitivity. So that's what an equivalence relation is, and yeah, there's not much more to it. Yeah, so let's try proving the theorems in the book. That those are quite important and will lead to more techniques. So let so in equivalence class, E is defined as y x, and it's defined in X, and ultimately it's going to be a subset of the A that the X is defined in. I'll just check one small thing. Yeah, so I was slightly confused. The R we're dealing with here is a subset of A cross A itself here. So that's what it means to be a relation on A. So in this case, it ends up making sense. So E of X is the sub Y in A such that, so because it's a relation on A cross A, if both the ordered pairs are going to, both the ordered pairs are going to lie in the set A itself. So if you take either the domain or the range, which can be defined for the relation, both of them are going to be a subset of A. So X is going to be an A because that's we're defining the equivalence class for a member of A, and every Y that's going to be related to X in any way is going to be a subset of A because R is a relation on A. So we're only dealing with relations on A so far. I don't so yeah, functions were the examples of relations on not one set, but both all of these are relations on the same set. But in generality, yeah, they need not be the same set. So because we're picking the other ordered one of the ordered members of the ordered pair, we're going to get a subset of A, right? And that's what we're defining. So yeah, this property alone is sufficient to conclude that it's a subset of A. And because X is a member of it. And of course, it's a property. So that's how we're defining the set. Again, same thing. And yeah, so yeah, X belongs to E of X because by reflexivity. Okay, so now let's try proving that E of X intersection E of Y not equal to phi implies what's the right expression here? Implies E of X equals to E of X prime, right? Hmm. Okay, so let Y belongs to this thing, right? So what does that mean? That means Y X and Y X prime, and this means yeah, this means X Y And by transitivity, this means x tilde x prime. Now what? Now, given this, we just have to show that their members are completely equivalent, right? So let W belongs to E of x. So W tilde x and x tilde x prime. So W tilde x prime. And this goes both ways, right? W tilde x. So, and you'll have to reverse it here. So we'll get this, and they're both basically equivalent formulas, and because of that, they're going to be equivalent sets. So yeah, if they're not disjoint, then they're going to be equal. That's the first theorem. So I used symmetry implicitly and transitivity just without mentioning it. So try to get used to that. Okay. Yeah. Now, so we have a set A and a partition on A, and a partition is a collection of subsets of A whose union is A. And union is we're defining union of A as taking on members of that. So it's the arbitrary union. It's not the other union. Okay. So union of A is equal to union of, how is it writing it again? Yeah. So I have seen people write this instead of this, and they're basically the same thing. So yeah, it contains all the members of each member of the collection. That's what ultimately it is. And if the union is equal to the whole set A, so in this case, people write A star and people write something else for this one. So it's the same. Yeah, just a notational issue. Don't get too hung up on it. Ultimately, yeah, if they're all disjoint and their union is the whole set, then it's a partition. And given a partition, we have to show that we can define an equivalence relation on it. So let me think about the exact formula for the equivalence relation. Okay, so I'm not sure if this is correct, but this is the best way I could formulate it. So since X and Y are members of A and we're defining their, yeah, so this is the best way I could think of formulating the equivalence relation. So since X and Y are members of A, there has to be some D in this collection D such that X is in D and Y is in some other D. And essentially they're in the same D. I mean, X is in D implies Y is in the same. The variables are the same, right? So that's the best way I could formulate it, and let's hope this works. Okay, so is this an equivalence relation? Let's see. So X belongs to D obviously implies X belongs to D. So we're fine with reflexivity, and by this statement, X must belong to some D, so we are fine. Ah, so we have the vacuously true problem here. But given the if and only if, I think we'll be fine. If they're both false, yeah, there's a bit of a problem if they're both false. I'm not sure. So I guess it's like, there has to be true too. So maybe add that condition if you can. Will that do it? Not sure. Or maybe some the other way around. So true implies false. So yeah, this ends up being, yeah, but what is that? I think there's a formulation, but now at this point, there's no point in drilling it to getting too deep into the details. Anyways, yeah, so reflexivity does follow, and the formula is wrong, but whatever. X symmetry is the case because of this, and so this is symmetry, and so if this is the case and this is the case by equivalence, yeah, it is transitive. Looks symmetric to me. But yeah, if you look at it in English, then it also works out. And because it's an equivalence relation, it's partial. Yeah. Hmm. So we get the collection of equivalence classes, right? And yep. they are going to be in the same member. So are they? Yeah, so they are indeed, the equivalence classes are indeed the set because X belongs to D, and can only if Z belongs to D, if and only if X tilde Z by the definition. So, and what does this mean? This means that they're in both the same set, right? Which is, so this means that they're in the same equivalence class, and this means they're in the same set. So they're both the same thing, right? Okay. Now we need to show uniqueness. So how do we show a uniqueness? Well, they're both the same D collection or the relation is identical. So the way to show a relation is identical. So X C one Y if and only if X C two Y, right? This is C, not anything else. Now, hang on. So uniqueness is easy. You just need to use the fact that we have EX1 and EX2. Basically, with both relations, you'll have different equivalence classes, and they'll both be equal to essentially D. Why would they both be equal to D? Because so because we just proved that the equivalence class generated by an element is precisely one of the members of the partition, right? And since they're both satisfying this property, they're both also equal. They're both equal to D, so they're both equal to each other, right? And since they're both equal to each other, what does that mean? That means y tilde x tilde 1x if and only if y belongs to E1. But that's if and only if y belongs to E2, which is if and only if y tilde to x. So they're equivalent. So whichever way you want, they line up. Okay, now we go on to order relations. So that's also three criteria, and that's yeah. So for order relations, let's see. I started with non-reflexivity, so x less than y implies x not equal to y. Next is transitivity, which is the same thing, x less than y, and y less than z implies x less than z. And the third is total. So it's another way of saying it is either x is equal to y, or x is less than y, or y is less than x. Or another way of saying it is x not equal to y implies x less than y, exclusive or y less than x. Both can't happen. Both can't also happen because otherwise by transitivity it will be reflective. So yeah, it's exclusive. Yeah, so that's the order relation. Is there anything else? Yeah. Immediate successor I will not cover, and dictionary order is defined. Yeah, largest element. So I'm just defining it one way, the other way is the same thing. So for a set A naught, a B belonging to A naught is the largest element if for all X belongs to A naught, X is less than equal to B. Now, if A is a subset of A naught is a subset of A, then B belonging to A now, not A naught, is an upper bound of uh, A naught if for all X in A naught, X is less than equal to B. But here, so the largest element, if it exists, the A is an upper bound too, but it need not always exist. What else? That's the upper bound. And if there exists such an upper bound, then it's bounded above. And if we take the set of all such upper bounds, which we can pretty much, we're implicitly using maximum comprehension here, but forget about that. If we take the least smallest element of all the upper bounds, then we get the least upper bound. Again, the smallest element need not always exist, so there's that problem. But yeah, then we get the least upper bound and or least greatest lower bound, and then we have the LUB and GLB property, which will prove to be equivalent. All right.